we're going to skip the warm-up and we're going to take a look at SI units. Okay, the SI system is an international system of units. This is actually the modern metric system, and it consists of a few base units, and this is primarily used throughout the world except for in a few countries, our country being one of them. And we tend to use this in science, and there are some rules that they tend to follow. I'm going to go over the bullet-pointed rules, and then you're going to do the quick check on the next page, okay? So generally speaking, unit symbols will be lowercase letters. The only time they tend not to be is if the unit is named after a person, okay? The one exception to this rule would be you use a capital L for liters. So moving forward on labs, if you've got something like milliliters as a unit, I would expect you to put a capital L for liters, okay? Okay. The full names of units are always written in lowercase. The only exception would be degrees Celsius. So when we're using the unit degrees Celsius or degrees Fahrenheit, make sure you guys put the degree symbol in front of that unit, okay? Also, unit symbols should never be pluralized. So you won't add an S onto the end of it. Like I wouldn't write milliliters like this. Do you know what I mean? That would be deemed inappropriate. Generally, if you've got a symbol at the end of a sentence, it would be followed by a period. We will be replacing the term mass with weight. We're replacing the term weight with mass. Okay, mass is a quantity of matter that stays the same no matter where we are. And then the symbol CC is something that doctors and nurses tend to write. CC is an abbreviation for cubic centimeters. We don't use that. We use milliliters or cm cubed. Okay. Also, if you have a value less than 1, put a 0 in front of that decimal point. It makes the decimal point stand out more. People don't question if it's actually there as much, okay? So I wouldn't write the 0.54 grams. Then in your book, you will see this rule performed a lot. You may also see this on Advantage. This is something that I don't make you do, but if you see a space in between 3 sets of digits, to the left and to the right of a decimal point, we usually put commas there, but the conventional way in the SI system is just to use a space. So 300,000 in your book is going to look something like this instead of the comma being there. Does that make sense? I don't care for you to follow this rule, like when we write up a lab report or something like that, but I'm just letting you know it's one of the rules in the SI system. And then we use decimal fractions instead of comma fractions in here. So for instance, on the lab, when you showed me the work to calculate the density of something in the pre-lab, you should divide those numbers out and get a decimal, and that would be your answer. Don't leave it as a traditional fraction. Then abbreviating things using the inappropriate symbol for things like seconds, okay? Seconds is just a lowercase s. You wouldn't write it as SEC. Or if we were using meters per second, you wouldn't write it as MPS. You would write it as M, because M is a symbol for meters with a slash and an S, like they have here. So just make sure that you're always using the appropriate abbreviations. And then if you're typing up a lab report, there is a space between the number and the unit. So for instance, 4.6 grams would be 4.6 with a space and then a G, okay? And then almost done. Instead of writing out the full word of a unit like grams or moles, which we'll talk about in chapter 3, you would use the abbreviation. So here they're showing you G for gram over mole, which is MOL, instead of writing out grams as a word and moles as a word. That would be deemed incorrect. And then lastly, when you've got temperature, remember the degree symbol goes in front of the C or the F, okay? Let's take a look at the next page. Do you want to do these together?
Yeah.
Okay. So here we're going to correct the errors that you see. Okay, you can just tell me out loud. Number 1, it says Ralph bought 6 kilos of potato salad. What's the mistake? What should I make that? kg. Good job. Number 2, the thickness of the oxide coating on the metal was 1/2 cm.
0.5.
Yeah, 0.5. But make sure you put the 0 in front of the point, right? And then what should I do with the unit?
No period.
No period. Just make it cm. Bless you.
Thank you.
Number 3, the weight of one, according to what is written here, that would be like megaliter of water is exactly 1 grams at 4 degrees C. What should I correct?
Milliliter.
Yeah, milliliter and grams. So grams would be G, milliliter should be lowercase m, capital L. Good call. How about over here? Capital C. Yeah, degree, capital C. Number 4, my teacher bought 9 liters of gasoline for her 883 cc motorcycle. Liters, we should put that as capital L. What else?
CC should not have periods.
Close.
Oh, should we capitalize? Oh, you used the 3.
cm cubed. Yeah? I don't ride a motorcycle, so you'll never see me buying gasoline for a motorcycle. Number 5, Rama's temperature increased by 0.9 degrees C, or C degree. 0.9, 0 goes in front of the decimal point, and then degree symbol goes in front of the Celsius. We good on that? Awesome. Let's move on to bigger and better things. Let's talk about accuracy and precision, okay? When we make measurements in lab, no measurement will be considered exact. It will have some uncertainty associated with it, which I will talk about in a second. But when we're taking a look at different measuring devices, the size of the opening can influence the precision of that measuring device. So here I've got my graduated cylinder, which has a relatively large opening. And then I've got a burette and a pipette with really small openings, okay? So the smaller the opening, the more precise that measuring device will be. And I'll go over the definition of precision in a second. So here it says that the burette and pipette are more precise than the graduated cylinder. So we could relate that to the size of their opening. Also, the division sizes that are on them, which are indicated by these individual tick marks that are here, okay? Those also help us decide how precise a measurement will be, and I'm going to teach you that today, okay? Also, they talk about how this would be like a meter stick or a ruler. And then I've got a caliper over here. The caliper has actually got much smaller divisions on it, so that makes it more precise than the ruler, okay, for determining length measurement. Now, let's take a look at uncertainty. There is technically only one exact mass in the whole world, and it's in France, okay? So in France, they have a kilogram, oops, wrong option. We have a kilogram, bless you, in a helium-filled bell jar, and that is the exact mass on the planet, and all of the other masses are measured in comparison to it. So that means all of the measurements that we make have some degree of uncertainty to them. This is shown on the next page. Okay, whoa, here's my bell jar in France with 1 kilogram inside of it, okay? Now, let's talk about accuracy versus precision. Accuracy is how close you are to the true value. So if you make a measurement, you measure the density of some metal, let's say it's a piece of brass, and then you look in a reference book and you find the true value or the actual density of brass, and you would compare the two, okay? So accuracy is often thought of as how close you are to the bullseye. So if I'm playing darts and I hit the bullseye, I'm accurate, okay? So here's my bullseye, bless you. If I hit it, that would be deemed accurate. Precision has two definitions, okay? Those two definitions are outlined for you here. And let me explain them. If I hit the bullseye constantly, if I'm throwing darts at a dartboard, one after the other, and let's say I keep hitting the same region with my darts, as long as they're close to each other, this would be considered precise. In the lab, if you keep measuring things over and over again, you keep reproducing those same measurements, they're all close to each other, that would be precise. Okay, so the reproducibility of a measurement would be precision or precise measurements. Precision also means how many places past the decimal are you allowed to record a measurement? Okay, so let me give you an example. Which one is more precise? 1.2 grams or 1.25 grams? Yeah, 1.25 grams would be more precise because I have more decimal places. Make sense? Okay. Okay. We're going to skip the quick check. Let's come down here to types of errors. Two types of errors. Systematic and random. If you are making measurements in the lab and you keep coming out above the true value or below the true value, that would be errors in the same direction. Those are systematic errors. So make yourself a note. Systematic errors would be either above or below the true value. They can't be both above and below. They have to all be above or all below, okay? Random error means you're going to have errors in high and low directions. So that means they're all over the place. So random error would be both above and below the true value. Okay? We're going to be spending the rest of class talking about reading volumes in graduated cylinders and lengths using centimeters and inches, okay? I'm going to go over the example on the next page, and then we're going to take a look at some practice problems and the worksheets that I gave you, okay? The worksheets that I gave you are not being turned in for a grade. You're just doing them for practice to help you get ready for the quiz on that topic next time. Does that make sense? So those worksheets have a front and a back, and can I stop this? We all have this? Okay.